Alright, what's going on, everybody? This video we're going to look at graphing uh, using calculus. We're gonna find where the function's increasing, decreasing, local max, min, concave up, concave down, inflection points, all the good stuff. Alright, so let's go ahead and get started. It's probably going to be a pretty long video. Alright, so the test for increasing and decreasing. Well, it says if f prime of x is greater than 0 on an interval, then f is increasing on that interval. And if f prime of x is less than 0 on an interval, then it's decreasing on that interval. All right, so the first thing you're going to have to do is when you start out doing all this stuff is you're going to have to find the critical numbers. And hopefully you remember that. That's from an earlier lesson. That's where you find the first derivative, set it equal to 0, and solve for x. So remember the critical numbers, that's where the first derivative is 0 or where the first derivative is undefined, provided that where the first derivative is undefined, the original function is defined at that point. Okay? All right, so the first derivative test, so now we know how to find increasing and decreasing. And if this stuff that I'm reading over right now, if it's kind of, that really don't make a lot of sense to me, don't worry about it too much. It'll clear up once we start working the problems. All right. So now the first derivative test. Suppose that c is a critical number of a continuous function f. If f prime changes from positive to negative at c, then we have a local maximum at c. And if f prime changes from negative to positive at c, then we have a local minimum at c. And then if f prime is positive on both sides of c, the left and the right, or negative on both sides of c, then f has no local maximum or minimum. All right, so let's look at this. We got two examples. We got this one and then we got this one down here. All right. And of course we've got more examples after that, but anyway, this one. Determine where the function is increasing and decreasing and find any local maximum and minimum values. All right, so our first function, we've got f of x is 3x to the fourth minus 4x cubed minus 12x squared plus 5. All right, so let's find our critical numbers. So we are going to find the first derivative. That's going to be 12x cubed minus 12x squared minus 24x. And we're going to set this equal to 0. All right. And solve for x. So let's factor out the greatest common factor. So that leaves us with x squared minus x minus 2 equals 0. So 12x times x minus 2 times x plus 1 equals 0. And so we have x equals 0, or x equal 2, or x equal negative 1. All right. So there's our critical numbers. So now let's find out where this thing is increasing and decreasing. So how do we do that? Well, we're going to do, what this says up here. And then when we find local max and min, we're going to do what this says. And it's easier than what it sounds. All right, so let's draw our number line and let's plot our points on the number line. We're going to plot our critical numbers on the number line. And in this case, it breaks the number line up into 4 regions. And what we need to do is we need to pick a number from each region. All right. So let's choose x equal negative 2, x equal negative 1/2, x equal 1, and x equal 3. All right. Now, you can pick any numbers you want. It doesn't matter. Okay, I just chose these. All right, you can pick whatever numbers you want as long as you choose a number from each region. All right, and now what we have to do is we have to evaluate the first derivative at each one of these numbers here. All right, now the -2, I can plug it into this one. Okay, or if I wanted to, I could plug it into this one. I mean, this and this are the same thing. It's just this one's factored. All right. So what I like to do, I like to take the numbers and plug them into the one that's factored because it's easier to evaluate. To me, it is. All right. So if I plug the -2 in, do you see if I do the 12 times -2, that gives me a negative number? And then if I do -2 minus 2, that's a negative number. And if I do -2 minus 1, that's a negative number also. So this would be a negative times a negative is a positive times a negative is negative. So this is less than 0. Now, I don't care. I don't care what the exact number is. Okay, I don't care. All I care about is it positive or negative. Because if you notice what it says up here, if f prime is greater than 0 or if f prime is less than 0, that tells us when it's increasing and decreasing. So that's all I'm concerned about. Is it positive or is it negative? I don't care what the exact number is. All right. So we get f prime of -2 is less than 0. So that means that this thing is decreasing. And go ahead and draw your arrows like that. All right, now let's do f prime of -1/2. So if I plug the -1/2 in, that's negative, and that one would be positive. -1/2 plus 1 is positive. So a negative times a negative is positive, times a positive is positive. So that's greater than 0. So here it is increasing. And then we have f prime of 1. Well, if I plug the 1 in, that would be positive there, negative, positive. So positive times a negative is negative, times a positive is negative. So this is less than 0. And so that's decreasing. And then we have f prime of 3. Well, that would be positive, positive, positive. So that's greater than 0. So that is increasing. So we can say that the function is decreasing from -infinity to -1 and 0 to 2, and it is increasing from -1 to 0 and 2 to infinity. So there you go. There's increasing and decreasing. Now look, if what I did right here, if that doesn't make sense to you, if you don't understand what I did, hopefully you do, but if you don't, well, then just take each one of those numbers, plug it into here, pop it in your calculator, and see what number you get. Okay, that's an option, but this is just quicker to do it with this. All right. Now they want us to find any local maximum or minimum values. Now, let's go back up here and see what it says. If it changes from positive to negative, a maximum, negative to positive, a minimum. All right, so, you can see here, it's changing from negative to positive. That's a local minimum. But look, it's right here for you. You see this? There's your local minimum. There's a local maximum, and there's a local minimum. See, if you draw the arrows like this, you see your local max and mins right there. Okay. So we've got, let's do our local minimums. So I have a local minimum at -1. Now, what do I need? Well, I need the y value of the coordinate. Okay. The local minimum and local maximum is a point. It's a point on the graph. So I need an x and y coordinate. This is where students mess up all the time. Okay, this is where they mess up all the time. For some reason, they will take that -1. Okay, they'll take this -1 and they'll plug it back into the derivative. Well, of course, if you plug it back into the derivative, you're going to get 0. But what are we looking for? We're looking for a point coordinate. We're looking for our y coordinate. So the -1, we plug back into the original function. This is going to give us our y coordinate, not this one. So make sure you plug it back into this one. All right. So if I do f of -1, that is going to give me, let's see. All right, so that is actually 0. Okay, now I plugged it into here. Okay, I plugged the -1 into here. So this is 0. It just so happens when you evaluate the original function at -1, it's 0 also. And then I also have a local minimum at 2. And so when I do f of 2, when I plug the 2 in for x into the original function, that gives me -27. All right. And then I have a local maximum at 0. And so f of 0 is equal to, well, when I plug the 0 into here, we can see that would be 5. All right, and so there's my local minimum and maximum values. All right. So hopefully that was, hopefully all that made sense. It's not difficult at all. I mean, the only calculus you're doing is taking this derivative here. That's it. The rest of it's algebra. All right. All right, so let's look at the next one. We have g of x is equal to x plus 2 sine x. All right, so let's take the derivative. So I have g prime of x is 1 plus 2 cosine x. So 1 plus 2 cosine x is equal to 0. So that's going to give me cosine x is equal to -1/2. All right, so here we go. Do we still remember our trig? All right, so we got cosine is equal to a negative number. So let's just kind of put that down here. Let's draw a little coordinate system. So cosine is negative. All right, so that means our solutions are in the second and third quadrant. That's where cosine's negative. Remember, all students take calculus. Second and third quadrant, that's our solution. Well, to get our second and third quadrant solutions, we need to do what? We need to find our reference angle. Remember, your reference angle is a first quadrant angle. So we have cosine x, and I'm going to use x prime. That's going to represent my reference angle. You may denote your reference angle something different. I've seen it different in a bunch of books. I've seen reference angles like this, I've seen this, I've seen this. However, it doesn't matter. I've been using the prime to represent the reference angle. So remember, whenever you take the sine, cosine, or tangent of a reference angle, it's going to equal the positive value, because remember, your reference angle is in the first quadrant. I guess I'm kind of giving a little trig lesson here too. And so my reference angle is, well, the cosine of what is 1/2? Well, that's 60 degrees, or what? Pi over 3. There's my reference angle. So I need to find my second quadrant angle. There's my reference angle. There's x. And so here x is equal to pi minus pi over 3, which that is going to be 2 pi over 3. And so I get x is equal to 2 pi over 3. And then I need to get my third quadrant angle. There's pi over 3. There's x. And so x is equal to pi plus pi over 3, which is 4 pi over 3. So that's going to be 4 pi over 3. All right, so now we need to put this on a number line. All right, so how about we do that right here. So I've got what? I've got 2 pi over 3, and I've got 4 pi over 3. So that's going to break it up into 3 intervals. And so I'm going to use x equals, so how about we do pi over 2, and then here x equals, how about pi, and then here we'll do x equal, let's see, 4 pi over 3, how about 3 pi over 2, I guess we can do that one. All right, that's the ones we will test. All right, so I've got g prime of pi over 2 is equal to, all right, so I've got 1 plus 2 times the cosine of pi over 2. Well, that's the cosine of 90, right? Well, one thing that we can do, remember this, you can sketch out your sine and cosine. Remember, that's pi over 2, and this is 3 pi over 2. That's cosine, and then if you want to sketch out sine, it's going to look like this, pi, oh, I'm sorry, that one up there is sine. This is the graph of sine, and then we can do the graph of cosine. That's pi over 2, and this is 3 pi over 2. All right. So what we have here is we need to evaluate g prime, okay, which is this right here. So the cosine of pi over 2, we can see that's 0. So that's going to be 1 plus 0 is 1, so that's positive. And so that's increasing. And then we have g prime of pi, which, let's see, pi, cosine's negative 1, so that's going to be 1 minus 2, that's negative, so that's less than 0, it's decreasing. And then I have g prime of 3 pi over 2. Well, cosine is 0 there, so that's going to make it positive, so that's increasing. And so we can see that this thing is decreasing from 2 pi over 3 to 4 pi over 3, and it is increasing from negative infinity to 2 pi over 3, and from 4 pi over 3 to positive infinity. So there's your increasing and decreasing. All right, now we need, excuse me, now we need the local max and min. All right, now we need the local max and min. But before we do that, I kind of did this on purpose, but kind of didn't. But let's go back for a minute and look at this. So obviously, you know, we get up here, and a lot of students will do this. This is kind of why I did it. And I'm hoping while you're watching the video, you might have said, oh, wait a minute, you didn't do that right. All right. So can you see what's wrong with my answer right here? This one right here where I listed increasing and decreasing. Well, we look at our number line and we say, yeah, okay, negative infinity to here it's increasing, here to here it's decreasing, here to here it's increasing. That's what a lot of students might think. But what do we have to do here? Do you notice that we need to erase this, and this needs to be what? 0, and this 2 pi. Do you see why we did that? It's right here. See that? We're only going to 0 and we're only going up to 2 pi. So be careful with that. Make sure you don't make that mistake, okay? I wrote it like that the first time to bring that point out. So hopefully you'll remember that, okay? All right, now we need local max and min. So you can see I have a local maximum here, a local minimum here. So my local minimum is going to be at 4 pi over 3. All right. So I need to do x plus 2 sine x. So let me erase this. Get some more room here. So we can go over evaluating this. I don't know. Hopefully you don't have problems evaluating your trig functions. But let's do this. G prime. So let's look at the local min for 4 pi over 3. All right. So we need our y value. So we've got g of 4 pi over 3 is equal to 4 pi over 3 plus 2 times sine of 4 pi over 3. And what does that equal? Well, you can punch that into your calculator, and that would give you 2.46. So this would be 2.46. And then we have g of 2 pi over 3. So that's going to be 2 pi over 3 plus 2 times sine of 2 pi over 3. And that is going to give us 3.83. And so our local maximum is 2 pi over 3, 3.83. And there's your local max and min. All right. So hopefully all that made sense. And look, we haven't even started graphing these things yet. All we're doing is finding increasing and decreasing local max and min. All right, so what do we have to do now? Well, now we have to determine concavity. When it's concave up, concave down, and all of our inflection points. All right, so let's look at that. So, concavity test. If f double prime is positive for all x and I, then it's concave upward on I. If f double prime is negative for all x in the interval I, the graph is concave downward on I. And we have a definition here, a point P on a curve, y equals f of x is called an inflection point if f is continuous there and the curve changes concavity. That's basically what this says, concave up to concave down, or it changes from concave down to concave up. Basically, if it changes concavity, there's an inflection point there. All right. So, before we get into graphing, we understand now that the first derivative, if it's negative, the function's decreasing. If it's positive, it's increasing. All right. And wherever it changes from negative to positive, there's a local max or min there. Negative, positive, positive to negative. There's a local max or min. And now we know the second derivative, it's positive, it's concave up, negative, concave down. And where it changes concavity, we have an inflection point there. All right. So what we want to do now is we want to be given some information, and we want to sketch the graph. All right. In other words, something like this. It says sketch a possible graph of a function f that satisfies the following conditions. F prime is positive on this interval, it's negative on this interval. It's f double prime is positive on this interval and this interval, and it's negative on this interval. And then we have some limits that it gives us. All right. And they want us to sketch the graph. All right. So let's see. Let's draw this, and let's go ahead and mark off some some numbers on the number line. So we're going to mark off the number 1, we're going to mark off the number 2, and then we're going to mark off the number -2, because you can see that's what we're dealing with. The number 1, and then we got -2, we got positive 2s, and so let's see what we can do with that. All right, so it tells us that from -infinity to 1, so from -infinity to 1, this thing is increasing. So what is it doing? Is it, is it looking like this right here? All right. Well, if we draw this, is it gonna go like this? Okay. Is it gonna go like this? What's it gonna do? Well, that's where we have to go down here to this F double prime, this concavity here. And so if we look at this, we can see from -infinity to -2. So from -infinity to -2, it's concave up, all right? But from -2 to 2, from -2 to 2, it's concave down. All right, it's concave downward. So if I draw this thing, what is it going to look like? Well, is it going to come way down here? What's it going to do? Well, notice here that as x goes to -infinity, it goes to -2. So that tells me there's a horizontal asymptote there, right? And I also have a horizontal asymptote, the x-axis, okay, at y equals 0. So when I draw this, I need to draw it in like this. Okay, it's going to come in like this. It's concave up. But notice from -2 to 2, it changes to concave down. So it's gonna kind of, I guess, kind of turn this way. I mean, I guess I could probably maybe try to draw this a little better. And then it's going to come up here like this. All right. And let's see, where at 1 it's going to start decreasing. So here it's going to start decreasing. So we know it's going to turn and come back down. And let's see, from -2 to 2, it is concave down because the second derivative is less than 0. So we know it's concave down. And then once it gets to 2, from 2 to infinity, and we also know from 1 to infinity, it's decreasing. All right, but look, from 2 to infinity, it changes back to concave up. And so it's going to look like this, and this graph is just going to get closer and closer to this axis here because we do have a horizontal asymptote here. Now, this is one. There's more graphs that you can draw, okay? When they give you information like this, the graphs can look different, okay? There's not just one right answer, okay? But yeah, there's your graph when they give you all that information there, all right? So, hopefully you got that. Hopefully that made sense. All right, let's look at this. The second derivative test. Suppose f double prime is continuous near C if f prime of C is equal to 0, so you got your critical number, and f double prime of C is positive, then we have a local minimum, and if f double prime is less than 0, we have a local maximum. That's the second derivative test. I never use it. I just use like so basically what they're saying is to determine if there's a local max or min. Remember how we did it in the previous examples where it changed from negative to positive or positive to negative when we found the increasing, decreasing. Okay, you do your local max and mins like that. But if you have this, then you can find the second derivative, which yes, we have to find the second derivative anyway to find concavity. So when we do the Second derivative, you just take those critical numbers and plug them into the second derivative, and if it's positive, it's a local minimum. If it's negative, it's a local maximum. All right. All right, so now that we've gone through all of that good stuff, now let's get to the good problems, the main problems here, sketching the graph. We want to sketch the graph. I got 3 examples here. All right, and I'm gonna go to a brand new sheet. Well, no, I just do them right here. Let's do number 1. I'll recopy the problem. We got f of x is equal to x to the 4th minus 4x cubed. So let's graph this thing. All right, so to graph this, we want to find out, where's it increasing, decreasing, local max min, concave up, concave down, inflection points, and then we'll sketch the graph. All right. So I've got f prime of x is equal to 4x cubed minus 12x squared. So 4x cubed minus 12x squared equals 0. So that's 4x squared times x minus 3 equals 0. So I get x equals 0 or x equal 3. All right, so there's my critical numbers. All right. So let's draw this on a number line. So I've got 0 and I've got 3. So I'm going to do x equal -1, x equal 1, and x equal 4. All right, so let's see what we've got. We've got f of -1. So I'm going to plug it into this one. So look, no matter what number I plug into this first part here, that's going to always be positive because the x is squared. So if we plug the -1 into here, that's a negative times a positive is negative. So that's decreasing. That's less than 0. That's f prime. And then f prime of 1, well, that's negative also. That's less than 0. And then we have f prime of 4. That is positive, so that's increasing. And so we can see that this thing is decreasing. It's decreasing from -infinity to 3, and it is increasing from 3 to infinity. So there's my increasing and decreasing. All right, so now we're looking for what? Local max min. Well, we have a local minimum and that's it. See, it doesn't change anywhere else. So I have a local minimum at 3, and then I need to do what? F of 3. And f of 3 is equal to -27. All right, so there's my local min. Now we need to do concavity. So for concavity, I've got to find the second derivative. So that's going to be taking the derivative of this. So that's going to be 12x squared minus 24x. So 12x squared minus 24x equals 0. So 12x times x minus 2 equals 0. So x equals 0 or x equal 2. All right. And so now for concavity, guess what? You do just like when you were doing increasing and decreasing. So we're going to plot the 0 and the 2 on the number line. So I'm going to do x equal -1, x equal 1, and x equal 3. And then we evaluate each one of these into the second derivative. Now I'm going to plug it into the one that's already factored because it's easier to determine if it's positive or negative. So f double prime of -1, let's say that's a negative times a negative is positive. So this thing is concave up. All right. And then we're going to do f double prime of 1. that's positive, that's negative, so that's negative, so that's concave down. And then f double prime of 3, that's positive, positive, so that's a positive, concave up. So concave down from 0 to 2, and concave up from negative infinity to 0 and 2 to infinity. All right, so there's my concavity. All right, now we have our inflection points. So inflection points, that's where it changes concavity. Well, where does this thing change concavity? It changes concavity at x equals 0 and concavity at x equals 2. And so I've got an inflection point at 0 and I have an inflection point at 2. Now, remember, this is a point. It's a point coordinate. So my inflection point, 0, and I've got to do f of 0. So you can see if we plug 0 back into the original, we get 0. And then f of 2, well, I plug 2 back into the original here, and that is going to give me negative 16. All right, so now we have found everything we need to find. Okay, we found everything. Increasing, decreasing, local max, min, concavity, and inflection points. And what I am going to do here is, let's see if I can grab this. Let's grab this and let's pull this down. I know it's going off the screen a little bit, but let's move it right. Let's move it right here. So now we have where we can see everything. So let's just kind of highlight what we need. We need this, we need these points, we need this, and we need this. That's what we need to sketch our graph. So let's see if we can come up some here. And let's just draw this right in here. That's the thing about doing these things, these videos. You don't have a lot of room on your screen. But let's see. What I like to do. I like to go through and plot my points I have. Okay. All right. So let's see. We've got increasing, decreasing, local min. Let's see. Did I grab everything? I guess I did. Okay. That don't look right there. Hang on. All right, never mind. That's right. I was just making sure I grabbed everything when I brought this down. All right, so let's plot the stuff. So we got the point. We got 0, 0. Okay, that's one of our inflection points. And maybe just kind of come over here and mark off 1, 2, and 3. And so 2, negative 16. So I'm going to say negative 16 is about right in there. And then I got 3, negative 27. We'll call that about right in there. Okay, this is not to scale. I know that, but you know, we're going to see what the graph looks like. All right, so what I know is from negative infinity to 3, this thing is decreasing. Okay, it's decreasing. And I think I might just move this point down just a little bit more. Maybe something like that. All right, so it's decreasing all the way up to negative 3, and then once I hit negative 3, it starts increasing again. But let's look at our concavity. From negative infinity to 0, it's concave up, and then from 0 to 2, it's concave down, and then it changes to concave up once I hit the 2 again. So it's concave up, and then it changes to concave down, and then it changes back to concave up. Now I know that, let me draw that again. I'm going to exaggerate it a little more than what I did. So it's all right, so it's coming in like this, and then it changes concavity again. So hopefully you can see that a little better. And then once it gets here, it starts increasing again, and see it's concave up from 2 on back to positive infinity. And so it's going to look like, and so there's your graph. Okay, I know that may not be the best looking graph, but it's good enough for this video, isn't it? All right, so that's that problem. All right, so now let's look at the next problem, number 2. Remember the 3 I had listed there? So let's look at number 2. That is f of x is equal to x to the 2/3 times 6 minus x to the 1/3. All right, so for this one, I'm not going to go into a whole lot of detail finding the derivatives. Okay, we got product rule. It's going to get messy. Okay, I'll do the first step on them, and then the rest I'll leave up to you. All right, it'll make the video way too long going through all the details of the derivatives. But remember, this is what? This is product rule. So the product rule says the derivative of the first function, so the 2/3 comes down, and that's to the negative 1/3 times the second function, plus the derivative of the second function, so that's 1/3 times 6 minus x to the negative 2/3 times negative 1 times what's the derivative inside the parentheses times the first function. All right, so that would be your first step there. And when all said and done, what you'll do is you'll put this x to the negative 1/3, put that in the denominator, and then this 6 minus x to the negative 2/3, put that in the denominator, get a common denominator and combine them. Okay, and your common denominator would be x to the 1/3 times 6 minus x to the 2/3. That would be your common denominator. And so after you do all that, you end up with the first derivative being 4 minus x over x to the 1/3 times 6 minus x to the 2/3. That's what you should get for your derivative. And that's, you know, that's good practice for you also. Okay, that'll be good practice for you. Now, let's find our critical numbers. So remember, f prime of x is equal to 0 when 4 minus x equals 0, right? A fraction is 0 when the numerator is 0. All right, so we get x is equal to 4. All right, and then remember, our critical numbers are also where the denominator is equal to 0. So that would be x equals 0 and x equals 6. See, 6 makes the denominator 0 and 0 makes the denominator 0. So here's our critical numbers, 4, 0, and 6. Now, before we go on and say, hey, these are our critical numbers, let's make sure they really are. So remember, the critical numbers, it says where the first derivative is 0, provided that those numbers are in the domain of the original function. So is 0 and 6 in the domain of the original function? Yes. So they're critical numbers. So now we make our number line. And so we've got 0, 4, and 6. So I'm going to do x equal negative 1, x equal 1, x equal 5, and x equal 7. All right, so when I plug these numbers in, I don't have to plug anything into this term because you can see it's squared. It's going to always be positive. Okay. So I just need to worry about this and this. So if I plug the -1 in, that's positive, that's negative, and that's positive. So that's negative. So that means this is f prime of -1 is less than 0. So it's decreasing there. All right. Now let's look at f prime of 1. So if I plug the 1 in, positive, 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 that's positive. So that's increasing. And then if I do f prime of 5, that's negative, positive, positive. So that's negative. So that's less than 0. And then f prime of 7, negative, positive, positive. So that's positive. So that's less than 0. So that's decreasing. All right, so this one, this kind of looks weird, doesn't it? All right, so let's see what we've got. We've got decreasing from -infinity to 0, and it's decreasing from 4 to infinity, and then it's increasing from 0 to 4. All right. And now what about local max and min? Well, we have a local minimum here. We have a local maximum here. And so we have a local minimum at 0, and let's see, we plug, that's going to be 0, 0. And then we have a local max at 4. And so f of 4, what does f of 4 equal? That is equal to, if you plug that in, that's going to be 2 to the 5/3. Okay, you can plug it into your calculator if you want, but that's what it would be, 2 to the 5/3. So that would be 2 raised to the, 1 point something. All right. So there we go. There's our local max and min. Now we need to find the second derivative. And I'm not going to work all of that out. But if we went to find the second derivative, if I did f double prime of x, let me bring that down. So if I do f double prime of x, you can see here, this is a nightmare, right? Quotient rule. So I'd have to do the derivative of this, which is -1 derivative numerator, times the denominator, which is x to the 1/3, times, let's take those parentheses off, x to the 1/3 times 6 minus x to the 2/3, right? Minus the derivative of the denominator, which is 1/3 x to the, let's see, what is that? That would be what, -2/3 minus 3/3. Yep. Times 6 minus x to the 2/3 plus, now this needs to all be in parentheses because we got to do the product rule down to take the derivative denominator. And then that would be 2/3 times 6 minus x to the -1/3 times -1 times x to the 1/3 times 4 minus x. And that is all over that denominator squared. And then you got to simplify it, okay? Shoot, I don't know. Like I said, I would probably write this as 1/3 x to the positive 2/3. I'd bring this down here with the 3. This one I would bring down with the 3. And then what I would do is I would multiply everything by x to the 2/3, 6 minus x to the 1/3. So that would knock those fractions out up here, and then you would have that down here also. Okay. So, but like I said, I'm not going to go through all that. That's too much work for this. That would be a video by itself. But once you do all that, you're going to get -8 over x to the 4/3 times 6 minus x to the 5/3. All right. So, all right. So that's what you'll get when you calculate the second derivative. So now we need to set the second derivative equal to 0, solve for x. Well, f double prime will never be 0, right? F double prime will never be 0 because it's only 0 when the numerator is 0, and you can see the numerator is -8. All right, but we still want to use where it's undefined. All right, so where the denominator is 0, we want to use those values to determine concavity. And so if I plot those, that's going to be 0, 6. All right, so x equal -1, x equal 1, and x equal 7. And so I've got f double prime of -1 not equals. All right, so we're plugging the -1 into here. So this term is always positive because it's raised to the 4th power. The numerator is always negative. And so we got to check with this one. So 6 minus -1, that's positive 7. So that's positive, positive, negative. So that makes the whole thing less than 0. So that's concave down. And then f double prime of 1, positive, positive, negative. So this thing is negative, so that's concave down. And then I have f double prime of 7. So that's going to be negative, positive, negative. That's positive, and so that's concave upward. And so I've got concave down. That is from what? That's from -infinity to 0 and 0 to 6. I'm going to split them up. You could write them all the same, but I'm going to just go ahead and split them up. And then we've got concave up. That is from 6 to infinity. All right, so there's concavity. Now let's look for inflection points. So inflection points. Well, that's where it changes concavity, and it only changes concavity here at 6. So we got to do f of 6, don't we? And what does f of 6 equal? Now remember, we're taking that, we're plugging that back into the original. So f of 6 is what? Well, that's easy. 6 minus 6 is 0. That's going to make the whole thing 0. So that was an easy one to do. All right, so here we go. We've got everything we need now. Okay, we got everything we need. You think this one's bad, you ought to see some of the ones you may come across, especially not in this section of graphing, but the next section when you got your rational functions. Those get nasty. I mean, this one's bad, but they get worse than this. All right, so let's see if I can get this. I want to move this down. All right, I want to move it down so we can see it. Let's see, will it fit right there? There we go. All right. So let's just kind of highlight what all we have here. There's increasing, decreasing, local max min, concavity, and inflection points. All right, so let's move this up. Let's see if we can't graph this thing halfway decent. All right, so I want to go through marking off my points and everything. All right, so I've got the point 0, 0. I've got the point 6, 0. So let's see, 1, 2, 3, 4, 5, 6. So there's 6, 0. I got that. And then I got 2 5/3. So let's just do 1, 2, 3. 2 to the 5/3, what is that? I don't know. Let's see. 2 raised to the 5 divided by 3. That's 3.17. Okay, so that's going to be a little bit more. Well, at 4. Let's see, we're here at 4. So that point's going to be about right in there. Okay, there's 2, there's 6, there's 0. All right, so let's see what's going on with this. All right, so let's see. From negative infinity to 0, this thing's decreasing. Okay. From 0 to 4, it's increasing. So it's decreasing, then here it's increasing. And then once it gets to 4, from 4 to infinity, it starts decreasing again. So let's see how I need to draw this in. So it's decreasing, but we also have to check concavity. It's concave down from negative infinity to 0. So that means, yeah, it's decreasing, but we've got to draw it in. We've got to draw it in like this. Let me draw that in again. Okay, it's concave down, but then at 0 it starts increasing again, and from 0 to, let's see, 2. Well, no, let's see. From 0 to 6 it's concave down, so it's not going to come. It's going to come in like this. So it's going to do like this. You see that? And there's our maximum. And we can see once it gets to 4, it starts decreasing again. And this thing is still, let's see, it's still concave down. Yeah, it's concave down all the way to 6. So it's going to look something like this. But look, once it gets to 6, it changes to concave up. So that means it's going to kind of tail off like this. And so there's your graph. All right. So, I mean, you can see these problems, I mean, they get bad. They get nasty. So, all right, let's hit the last one. Last problem. All right. So this one doesn't look bad, but you never know. All right, so let's see what we've got here. All right, so we need to find increasing, decreasing, concave up, concave down, inflection points, local max, local min. But with this one, notice what we have here with this one. We have 1 over x, and 1 over x there in the exponent. It's undefined. Okay, this function's undefined at x equals 0. So we're going to need to look at to see if we have any vertical asymptotes. Okay, that's what we're going to need to look for. See if we have any vertical asymptotes. So do you remember how to do that? And we're going to look for horizontal asymptotes also at this fraction here. So let's do that first. So let's do the vertical asymptotes. So we know this undefined at x equals 0. Well, we've got to see if there's a vertical asymptote there. And the way we do that, remember, this is back at the beginning of your calculus class. You got to take the limit as x goes to what? 0 from the right. And so that's e to the 1 over x. All right, so as x goes to 0 from the right-hand side, that is going to be what? So we're putting in numbers close to 0, so that's going to make this exponent blow up, it's going to go to infinity, so that goes to infinity. You see that? All right, so what does that mean, that we have this limit equal infinity? Well, that means that there's a vertical asymptote there. Remember, if you take the limit as x approaches a number from the left or the right, and it equals plus or minus infinity, or if the limit as x approaches that number equals infinity, then you have a vertical asymptote there. So we've established there's a vertical asymptote, but what we also need to do is do the limit as x goes to 0 from the left of e to the 1 over x. So we need to do that also. Now, this is not going to show that, hey, there's a, it's not going to show that there's a vertical asymptote. We've already done that. But when we're drawing the graph, we need to know how to draw it. What's that graph going to look like when it's coming into 0 from the right and when it's coming into 0 from the left? We want to be able to see that. So what happens here is we come in from the left-hand side. All right. All right, so you can see that as x gets closer and closer to 0 from the left-hand side, this thing is going to what? Negative infinity. And so if we take this term and we move it down to the denominator, remember that becomes, it's like it's going to positive infinity. So we have 1 over something going to positive infinity, and that would equal 0. Okay, so we know we have a vertical asymptote at x equal 0. It's not because of this, it's because of this up here that we have a vertical asymptote, because it equals infinity. We just want to see, what does this function do when it comes into 0 from the left. As we approach 0 from the left, the function is approaching 0. All right. Now let's look at horizontal. Asymptotes. All right, so remember to do that. We take the limit as x approaches infinity and negative infinity. So, I mean, it's going to be the same for both of them. As x gets larger, this is the exponent's going to 0, so that's going to equal 1. And then the limit as x goes to negative infinity, e to the 1 over x. Well, that's going to go to 0, or negative 0, which is just 0. That's going to equal 1 also. So we have a horizontal asymptote at, not x, at y equals 1. So there's your vertical and horizontal asymptotes. All right. Now we can start doing increasing, decreasing, and all that good stuff. But let's keep a note of these two values, because we'll have to put those on the graph. All right, so now I got f prime of x is equal to, so I'm taking the derivative of e to the 1 over x. So remember, that's just e to the 1 over x times the derivative of the exponent, which is negative 1 over x squared. So I get f prime of x is equal to e to the 1 over x squared, and that would be, let me write that again so I can squeeze that negative in there, e to the 1 over x squared. So there's my derivative. So remember, what we do is we set the derivative equal to 0. All right, well, f prime will never equal 0, okay, because it's 0 when the numerator is 0, right? Well, the numerator will never be 0. Okay, it'll never be 0. And then we also have critical numbers where the first derivative is what? Undefined. Well, the first derivative is undefined at 0. But the original function is also undefined at 0, so there's no critical numbers. Okay, that's the difference. Remember the last problem? The first derivative was undefined at those values, but the original function was not. Okay, it was not. So that means those were critical numbers. But in this problem, the first derivative is undefined at 0, but the original function is also undefined there. So there are no critical numbers. So now to do increasing and decreasing, we're going to plot 0 on the number line. So even though 0 is not a critical number, the first derivative is undefined there. So we're going to test it at where it's undefined, because it could change increasing and decreasing there. So x equal -1 and x equal 1. We're going to plug that into here. Well, really, there's no need to, is it? Can you see that? But I'm still going to go through the process, because it's not going to work like this all the time. Okay, it's not going to work like this all the time, but in this case it does. Can you see that no matter what number we plug in on the number line, that the first derivative is always going to be negative? It's always going to be negative. Well, because think about it, this exponential part, that's always positive no matter what you plug in for x. This squared term, it's always positive no matter what you plug in for x. And since this fraction here is always positive and we've got the negative, that means it's always negative. And so that means this thing is always decreasing. So this thing is decreasing from -infinity to 0 and 0 to infinity. Now I'm going to split it up here because the function's undefined at 0. I'm not going to say it's increasing. I'm not going to say it's decreasing from -infinity to +infinity. I want to put that gap in there because it is undefined there. And then local max min, you can see there's none. There's none there. All right, so now let's look for concavity. Okay, so we need the second derivative for that. So the second derivative, and once again, I'm not going to work this all the way out, but I'll do that first line for you. So that's negative, and so this is I'm going to put that negative out here, and then quotient rule. So that's the derivative of the numerator, which is e to the 1 over x times the derivative of the exponent times the denominator minus the derivative of the denominator times the numerator, and that's all over the denominator squared. And when you simplify that and everything, you end up with e to the 1 over x times 2x plus 1 over x to the 4th. All right, so there's our second derivative. So we need to find when is the second derivative equal to 0. Well, that's when 2x plus 1 equals 0, or x equal -1/2. All right, so we're going to test that on the number line. So we've got the -1/2, and we're also going to test where the second derivative is 0, or where it's undefined. We're going to, not 0, but where it's undefined. So we've got, let's see, we've got x equal -1, x equal -1/4, and x equal 1. All right, so I'm going to obviously plug all of these into here. But look, you don't have to plug it into everything, because you can see the -1, when we plug it into here, it's positive. When we plug it into here, this is going to be positive. So the only thing we've got to check is here. So if we plug the -1 in, that's a negative, positive, positive, that's negative. So that's concave down. And then f double prime of -1/4, that's a positive in here, positive, positive, that's greater than 0, that's concave up. And then f double prime of 1, that's going to be positive also, that's concave up. And so we have concave down, that is from -infinity to -1/2, and we have concave up, that is from -1/2 to 0, and I'm going to split these up, 0 to infinity, concave up. All right, so now we have inflection point. We have an inflection point at -1/2. So -1/2 and f of -1/2. F of -1/2, that's going to be e to the 1 over -1/2, which that's e to the -2. All right, so there's our inflection point. So let's go back up here and let's grab the, where did it go? Well, we had it earlier, didn't we? Okay, so it's not there. So anyway, we had increasing and decreasing. So remember, this thing was decreasing from -infinity to +infinity, right? So decreasing from -infinity to 0 and 0 to infinity. Remember, it's decreasing the whole time. See right here, and I split it up into the two intervals. All right, so now let's look and see what, and then as far as local max and min, there was none there. So let's see if we can draw this thing in. All right, so from back up here, we know we have a vertical asymptote at x equals 0. We have a horizontal asymptote at y equals 1. So let's maybe sketch those in. 1, 2, 3, 1. You know, I'm gonna make these a little wider. Let's put the 1 up there. And so we got a horizontal asymptote here. And then of course we've got our vertical asymptote here. All right. So what is this thing doing? Well, from -infinity to 0, this thing is decreasing. And let's go ahead, let's put the 1 there. And then we know here we've got -1/2. Let's plot that point there, -1/2 e to the -2. Okay. So I know from -infinity to 0, this thing is decreasing. Okay. Well, from -infinity to -1/2, it's concave down. Okay, so I know I got to draw it in like this. But look at this. Once it hits -1, from -1 to 0, it's concave up. So it's going to change concavity there. All right. But now we need to know, what is this graph doing when x is getting close to 0, and that's coming into 0 from the left. So when it's coming into 0 from the left, it's approaching 0. And so we'll have an open circle there. Okay. That's why you want to make sure you check these things. You want to take those limits coming in from the left and from the right. Okay. So you know what that graph looks like. So now let's jump over to the other part. So you can see as x goes to 0 from the right, the function's going to infinity. And as x goes to infinity, it's approaching 1. And we can see as x went to -infinity, it approached 1 also. So, and then also from, let's see, from 0 to infinity, this thing's concave up. So we know it's going to infinity there, and then as it comes this way, it's approaching 1. And there's your graph right there. All right, so I don't know about you, but I'm glad that video's over with. That was a long one. All right, so hopefully it helped. I mean, you know, a couple of these, they were pretty nasty. I mean, this one wasn't that bad. I think the one before this one, that one was the worst one, especially finding those derivatives, man. Hopefully your teacher won't give you anything nasty like that on the test. But, you know, there it is. To graph these things, you got to find increasing, decreasing, local max min, concave up, concave down, and any inflection points. That's what you got to find. And then sketch the graph based on all that stuff. I see students when they take the test and a problem like this is on there, I see this all the time. They're missing it. Okay, but just remember, that's all you have to do. Okay, just those steps. Increasing, decreasing. Well, first, find the derivative, find your critical numbers, and then use those increasing, decreasing, plot them on the number line. Then you got your local max min. Then you take the second derivative, set it equal to 0, plot those numbers on the number line. That's going to determine your intervals of concavity, and then wherever it changes concavity, that's your inflection points. So hope the video helped. I don't know how many of you are still watching now or how many of you have watched this far, but if you are, good. Leave me a comment, let me know. But thanks for watching. Check out my other videos. Give me a like, share, subscribe. I'll see y'all later.